All right, we're starting here with example number 4. So you can see I have a radical, but it's in the denominator, and I really have to simplify that and get that out of my denominator, but I also have this big other fraction. So there are several steps to complete when solving a problem like this. The first step is to find the conjugate of the denominator. In order to do that, I just switch the sign that's in between my two terms. So for this problem, since it's 5 plus the square root of 3, the conjugate is going to be minus the square root of 3. Once I find that conjugate, I multiply the entire fraction by that conjugate over itself. And the reason I can do this is because anything divided by that same thing is 1. So mathematically, I'm not really doing anything to the problem. I'm just kind of simplifying things. So then I can just go ahead and multiply my fraction. And when I multiply fractions, I multiply going straight across. So my numerator just becomes 1 times what that conjugate was 5 minus the square root of 3. The denominator simplifies a lot nicer. So I take that first term and I square it, and then minus. It's always going to be a subtraction, no matter which one is positive and which one's negative. The denominator in the answer will be negative. And then I take the second term and I square it as well. So then I can just go ahead and simplify. So I just distribute whatever's in the numerator to both terms. So I end up with 5 minus the square root of 3. And then I can simplify the denominator. And I can do that because I know that 5 squared is 25. And I know that the square root of 3 squared is 3, right? Because these are inverse operations of each other, and so they kind of just cancel each other out. So I know that 25 minus 3 is 22. So now that I have a denominator with a number instead of a radical, I'm as completely simplified as I can be. And there's nothing else that can go away. So there's that one. Okay, so we're going to look at these two and write them all in their simplest form. Now these are using different steps that we've done so far. Okay, so what we see here is actually what's example 3 in your book. So we're trying to write our expressions in simplest form. Okay, so let's look at A first. So I look and I'm taking the cube root of 135. So I want to factor out my perfect cube. And the way I can do that is I know that 27 is a perfect cube because 3 times 3 times 3 is 27. These are just some of those numbers that we have to know. Just like 8 is also a perfect cube because 2 times 2 times 2 gives me 8. But for this one, we're going to use 27. So then I can use my product property of radicals to separate them out, to split them out, and then I can simplify. Because I know this first term is a whole number, it can simplify into that whole number. So let's look at B. Okay, I have to take this denominator and make it a perfect fifth power. And I know that I can do that by multiplying by 4, because that will be my perfect power right there. So what I end up with is once I multiply, and again I can do this because it's the same thing on the numerator and the denominator, which equals 1. So then I use my product property and I simplify. So here we go. Here's our next example. We're trying to simplify each expression. So for part A, I see that what's inside my radical is the same on both, and it's taking it to the same root. So all I do is I can pull out whatever's in front of these. So this is like saying I have 1 apple plus 7 apples. So I just add those two terms together and I end up with 8 apples. I can do something very similar with part B. Because my base is the same and my exponent is the same, I go ahead and I take out the values in front and combine them. For part C, I have to do a couple of steps beforehand. I first have to simplify this 54. So I know, going back, we're looking at our perfect cubes. So I know that this 54 can be broken down into the cube root of 27, right, which we said was one of our perfect cubes, and the cube root of 2. So this can then further simplify because I know the cube root of 27 is 3, and then I have the cube root of 2. So now that I have that, I've got 3 cube roots of 2 minus 1 cube root of 2, which will give us our final answer. So here's where I can just simplify and continue to move on. Right, so they just showed these steps in a different order, but we did the same exact thing. Okay, so I want you to take a minute and solve these problems right here on your own paper. All right, here is our next example. We are told to simplify each expression, and we see that we're finding the cube root of 64 y to the 6th. So the first thing I want to do is I want to separate out any of my perfect cubes that I can, right? So what I can do, and so I start here with my number. I want to look at everything separately. And I know that 64 is one of my perfect cubes. It's 4 times 4 times 4. So I can just write that a little simpler, and I can go ahead and simplify my variable as well. So then once I go ahead and I separate them, again, my cube root and my cubed cancel each other out. Same thing with this term. My cube root and my cube cancel each other out, so I'm left with 4y squared. So for part B, I do something similar. I want to look at each term separately. So I'm going to start with the x values. Okay. Using some of my properties, I know that if there's an entire fraction underneath my radical, I can simplify that into the numerator and the denominator. So the numerator is already pretty simple for me, right? And then the denominator, I have to do a little bit of simplification, and I can pull that 4 out of here because I know that it's 2 times 4. And this is what we have. I have to use the absolute value sign because of my different properties that we learned back in section 1 about how many roots we have. So again, I'm looking at a bunch of different values underneath my radical sign. So I want to just simplify it as much as I can, and I want to look at one thing at a time. So for A, I factor out my perfect fifths, and I can do that. I can't do anything with the 4 because I can't multiply anything times itself 5 times to get 4, so I just leave that alone. I know that a to the 8th can also be written as a to the 5th times a cubed, and I can simplify everything a little bit further. So I first factor out those perfect fifths, and then I separate them out a little bit further. Using my properties of radicals, I can pull out everything that can be factored out, so then I can simplify and have my final answer. Okay, I can do something very similar with B. And again, we see we have a radical in the denominator, which we don't like. So I go ahead and I multiply that out, and I can do this because this term right here is 1, so I don't actually do anything to the problem. And then I use my product property and I multiply, and then I simplify. So for part C, again, I look at all of my just separate numbers. So I start with the numbers first, and I know that I can divide 14 by 2, and that will give me 7. Then I look at my x values, and I know that my exponent here is 1, and I know when I'm dividing, this is back from section 1, I subtract my exponent, so I have 1 minus 3/4. I look at my y's, I only have that one y value in the numerator, so it stays there. Then I look at my z's, and I don't like negative exponents, remember. To get to a positive exponent, I just move it to the numerator, and I multiply it by negative, so it becomes positive. And then I can just simplify from there. Okay. So again, I'm simplifying. Go ahead and take 1 minute and do these problems on your own. Here are some more problems that you can just practice on. These answers I can give you. If you want them, please let me know.